Okay, so we should be live. Hello and welcome everyone to the Linera Autumn Dev School. I'm Christos, I'm a software engineer at Linera, and this is the first coding workshop. What we're going to be doing is we're going to be building a fungible token application on the Linera network. And if you joined the previous dev school, the summer school, the tutorial is going to be very similar to last time. The workshop is going to be very similar. There are some minor updates to correspond to the SDK 0.4 version, which we released recently. So you can watch it again just to for a refresher, but you should be good mostly. The workshop is about 45 minutes. And it's pre-recorded because, the demo gods, things don't always go well. So I pre-recorded everything just to make sure that everything works. And if you have any questions, put them in the chat. I'll be around to answer any questions you may have. And I'm just gonna go ahead and start the video. So I hope you guys, I hope you enjoy. Hello and welcome everyone to the first coding workshop for the Linera Summer School. My name is Christos, I'm a software engineer at Linera, and today what we're going to be doing is we're going to be building our first application on Linera. And the application we're going to be building is the fungible application, the so-called fungible application, which is pretty much an ERC20 token or something equivalent to that. So it's an application where you can mint tokens and transfer them onto different accounts. Now, some kind of assumptions going into this. I'm going to assume that you know some Rust. We're going to be programming primarily in Rust, and I'm not going to be covering the semantics of the language. So if you don't know any Rust, there's some really good resources out there, like the Rust book and so on, where you can get up to date on the language. The second assumption is that you know a little bit about Web3 and blockchain. Now, understanding the specifics of the Linera multi-chain programming model is not necessary. We're going to kind of get into that together, but understanding what a blockchain is, how it works, and so on, it's going to be super useful. Finally, I'm going to assume that you've already cloned the Linera protocol repository and it's checked out on your machine. Okay, so now let's go ahead and download and install the Linera binaries. And to do that, we're just going to use cargo install Linera service. And what this is going to do is, well, I already have it installed, but it's going to install the Linera binary, which is used to interface with the network, as well as the Linera server and the Linera proxy binaries, which essentially enable you to spin up local networks. And just to check that you have the Linera binary correctly installed, you can do linera --help, and that'll bring up the help dialog as usual. So now what we want to do is we want to build a new project. We're just going to create a new project for our fungible application. And to do that, we're going to use the Linera project new command, and we're just going to call it fungible. And what this is going to do is it's going to set up the scaffolding of our project, the contract file, the service file, the librs file, and we'll get into that a little bit. It also sets up your cargo.toml with all of the required dependencies to build Linera applications. And just to check that everything works, we're going to quickly do a cargo build. And it's going to fetch certain crates from crates.io, and hopefully it should build the binary. Okay, so now that we've built the binary, let's open it up in our IDE and take it from there. Okay, so now that we have our application open in our IDE, the first thing we want to do is take a look at the structure of the application. So first we have our contract file, which defines the smart contract for the application, and it implements the contract trait, which is defined in the Linera SDK. Ignore the red lines here. This is just my IDE hallucinating, I think. And we have all of these methods, which we'll get into: initialize, execute operation, execute message, and so on. Next, we have our lib.rs file, which defines our contract's application binary interface and our services application binary interface, which are essentially the types that interface with our application. Next, we have the service file, which a service is essentially a read-only view into our application. It is a kind of non-metered queryable interface into our application, so we can get data from our application if you want to query it from a front end or something like that. And finally, we have the state RS file, which is the state of our smart contract. For now, it's just called application, and it consists of a singular value of type register view, which again, we'll get into in a little bit. Now, the first thing we want to do is we want to publish this application to the network, but we don't really have a local network running yet. So we'll create one. And to do that, we can use the Linera net up command. And what this is going to do, it's going to do a few different things. So first of all, it's going to create a Linera validator locally on our machine. It's going to consist of 4 shards. And also what it's going to do is it's going to create the Genesis configuration for this network, which consists of only one validator. It's also going to create a wallet file, which we're going to use to store things like chain IDs, keys, and so on. And the storage, which is a database that we're going to use for our client. And again, more on that in a little bit. So what we're going to do is we're going to take these two export statements. We're going to copy them. We're going to create a new terminal here. And we're going to paste these here. And now if we do something like Linera sync balance, oops, that's one command, Linera sync -balance, we should see that the Linera binary spoke to the validator, synchronized chain information with the validator, and also updated all of our user chain states. And to see the contents of the wallet, we can use the Linera wallet show command, which is going to show you all of the different chains that you have currently, the latest blocks for all the chains, the public key, the owner, and there's one green chain here, which is your default chain. And the reason you have a default chain is so that you don't have to explicitly specify a chain ID every time you want to perform an operation. Sometimes you're dealing with a singular chain, and all of our operations take an optional chain ID parameter, but if one is not specified, it'll just use the default chain ID. So what we want to do now is we want to publish the fungible application on the network. And to do that, we're going to use the Linera project publish and create command. And we're going to give it an initialization argument to get started. So an initialization argument is used to seed the state of the application. And you can find the type of your initialization argument under contract ABI initialization argument. Right now, it's the empty tuple because our application doesn't have any behavior yet. And that empty tuple kind of corresponds to just the null JSON here. So we're just going to specify that real quick. And this is going to build our application locally, compile it to bytecode, and upload it to the network where it's going to be accessible. Okay, great. And the bytecode for application was published successfully. And the application was also created successfully, which references the bytecode we just uploaded. And below that is the application ID, a unique identifier in the network, which points to our application. So now to explore our application state, we're going to use the Linera node service, which is essentially a local web server that opens up a GraphQL, which serves a GraphQL ID, which is then accessible via your browser. To start the Linera node service, we're going to use the Linera service command. And this is going to ask us if we want to open up the GraphQL ID on port 8080. Perfect. And here's my GraphQL ID. On the left here, you can look at all of the different types that we expose and the schemas that are available. So for example, we have the query schema, mutation schema, which allows you to execute system level operations and things like that. But all we want to make sure is that our application is now on the network. And to do that, we're going to run a query and query the existing applications. And for those applications, we want the ID, a description, and the link to the application. And there we go. Here's our data. It's a vector of applications because obviously there could be more than one application on the network. This is the ID of the application, which is the same ID that we saw here. The bytecode ID, which is, again, this kind of opaque reference to a blob of bytecode on the network. And this is essentially the WASM, the compiled WASM from our project. The certificate hash of the block and the chain that it was deployed on, which is the same as our default chain, E47, E47. Great. So now that we've successfully published an application on the network, let's build our fungible app. Okay, so now that we've deployed our Hello World application, let's start building our fungible application. So whenever I'm kind of building a new application on Linera, I like to start by defining that application's binary interface. Essentially, what is the behavior of my application as is expressed through the type system? And the two types that we're going to be primarily dealing with are called operations and messages. So operations are defined by an application developer, and each application can have a completely different set of operations. Chain owners then actively create operations and put them in their blocks, in their block proposals, I should say, to interact with an application. Now, in our case, the operation, we only have one operation right now, which is the transfer operation, which is when I, as a chain owner, want to transfer money from my chain to your chain. So let's build out that operation. We'll call it operation, and we'll create an enum pub enum operation here. And our operation is going to have a single variant called transfer. And we're going to be transferring money from an account owner, so of type owner. And this owner is a primitive type defined in the Linera SDK. We're going to be transferring an amount. So how many tokens are we transferring, which is going to be of type amount, which is basically a non-negative integer or amount of tokens. And finally, we're going to have a target account, which is going to, not to be of type owner. You would expect it to be an address that we're sending tokens to, but in fact, we are sending tokens to an address on a given chain. And so we're going to call this type account, and we haven't really defined account yet, but we'll define it here. Pub struct account is going to be, it's going to have a chain ID, pub chain ID, and it's going to have an owner. So the owner of the account, we're going to call it owner. Okay, so now that we've defined our transfer operation, the next thing we want to do is think about how we're going to send money from one chain to another. And this is where the concept of messages comes in. So a message in Linera is a way that a chain can talk to another chain. And what we want to do is if I want to send money to someone, I, as the owner of, say, chain A, want to execute an operation on chain A, which is going to say transfer money from my account to a target account on chain B. So account B, let's say, on chain B. And to do that, we are going to define the credit message, which is going to say, I am going to increment the value of your account on chain B by the amount that was specified in my transfer operation. So to do that, we're going to define the message enum. I'm just going to call it message, pub enum message. And this is going to have one variant, the credit variant, which is going to take an amount, the amount we're crediting the recipient's account by, and which account is receiving this money. So that's going to be a owner, a recipient address. And that's basically the ABI of our application done. One thing we're going to do quickly is we're going to rename this from fungible ABI, from application ABI, to fungible ABI. And next, let's move on to our application's state. The state of the application in Linera is defined by convention in the state.rs file. Now, in a regular Rust application, if you want to, let's say, store some data in memory, what you would do is you would define a struct, we'll call it myState, and in this struct you would have various fields that correspond to whatever data you would like to store. Now, the problem with this is that this is all in memory, and as soon as your process dies, all of this state gets wiped. What you would need is, in the background, some sort of database where you can save your changes, or maybe you want to serialize it to a file or whatever. Now, in Linera, we use a different paradigm for storing our application state that we've developed in-house, and it's called views. And views are really, really cool. They are basically like an ORM, and what they enable you to do is make a bunch of mutations to your state in memory, and then all of those mutations get rolled into one and committed to an underlying data store, meaning that you don't need to think about your application. You don't need to think about how data is being stored. It gets all done for you in the background. Now, if we think about what we want our application state to look like, if we were just doing it in vanilla Rust, maybe it would be like something like accounts. And we would use, let's say, a hash map or some sort of map structure from an owner, from an address to an amount, because we want for every address on our application, them to have a balance. So for every address, we have a corresponding amount. Now, under the view system, what this looks like is we're going to change this value right here to accounts. And we are going to use a map view here, which basically corresponds to a B-tree map. And we're going to have it from owners to an amount. I'm going to import those variables quickly. Next, we want to define the API of our state. That is, what set of operations does the contract execute on the state? And to do that, we're going to create an impl block, impl application. And in fact, we're going to change, just to adhere to some conventions and remain consistent throughout our code base, we're going to rename our application to fungible. Perfect. So the first operation that we want to expose over our state is the operation initialize accounts, where we are going to, when our application is first deployed to the network, we're going to initialize accounts to a certain value. And we're going to pass a mutable reference to self because we're mutating the underlying state. We're going to pass it a certain owner who is going to be the creator of the application, and an amount, which is what their account, what their initial account balance should be. So what we're going to do here is we're going to say self.accounts.insert, because right now our balances are empty. And we're going to say for a given owner, we're going to give a given amount. And this is a fallible operation, but let's just ignore that for a little bit and say, okay, if we failed to insert into our accounts, we're just going to say error in insert statement. Cool. And why is it complaining here? Okay, the size is not known at compile time. I think this is fine. I think this is just my IDE complaining. Next. We want to expose the balance for a given account. So we're going to define pub async function balance. We're going to take just a reference to self because we're not mutating anything. We're just reading. Give it a reference to owner. Oops, that should be capitalized. And for a given owner, we get back an amount. Okay, so we're just going to read from our view, get count. Await, because this is a asynchronous method, and expect failure in retrieval dot unwrap or default. Perfect. So basically, if we don't find an account, we'll just return 0 because the default implementation of account returns 0. The next operation we're going to want to expose is the credit operation. So when we give money, when we give some tokens to someone, we want to credit their account. Again, it's an asynchronous function. Whoops, pub async fun credit. Again, we're mutating the underlying state, so we're going to take a mutable reference to self, count, owner, and an amount by which we're crediting. And we're going to get a mutable reference to our balance, self.balance count, await, and we are going to perform an addition to that balance, balance.saturating add, saturating add just being essentially a method that is not going to panic if we exceed U128, I believe. And we're going to increase it by an amount. We're going to increase the balance by an amount. And finally, we are going to insert that back into our accounts. Self.accounts.insert into the account that we care about, the balance, and expect, failed to insert. Okay, perfect. And the last function we need that's going to, the last function that we need to interact with our state is the debit function. So this is going to be taking away some money from a given account. So pub-async function debit. Again, we're mutating the underlying state, so we'll take a mutable reference to self for a given account, a given amount. And we're going to get the balance for that account again, self.balance and account.await. Balance, gonna try sub-assign. It's just gonna reduce it by a given amount. And then we're going to map, and if that fails, we're gonna map the error into an insufficient balance error, which is an error type we haven't defined yet, but we will soon. Oh yeah, and this should be a result because debiting can fail. Although crediting cannot fail, a debit can fail because the amount you debit could exceed the balance that you have. So we're going to make this a result type where the error variant is insufficient balance error. Perfect. And finally, we want to insert that balance back into our accounts. So insert for a given account, a given balance, and then again, fail if the operation failed to insert, and then we're just going to return OK. Now here we haven't defined the insufficient balance error yet, so I'm just going to quickly define that. Obstruct insufficient balance error. We're going to be using the this error crate here, so we're going to define the error attribute that it needs, or the error annotation, sorry, that it needs. Insufficient balance error. And we need to derive all the things that, so we're going to need clone, copy, debug, and error here. And I don't think we've imported this error, so I'm going to import it here and use this error. And that's our state done. Okay, so now that we've finished our state and we've defined all the ways that you can interact with it, let's get to the meat and potatoes of our business logic, which is in contract. So the contract trait, okay, our Linera application is broken down into two parts. The first is the contract, which is the metered part of the application that actually performs computations and mutates the state of your application. The second part is a non-metered read-only view into your application, which is called the service. And we'll be using both of these, but we're going to start with the contract. And the way you define a contract on Linera is simply by implementing the contract trait, which has 5 methods. We won't be using all of them. In fact, we'll only be using initialize, execute operation, and execute message. So initialize happens only once in the entire lifetime of the application when it's deployed on the chain on which it's originally deployed. And this is where you specify things like, okay, how are we going to use the initialization arguments and so on. Execute operation is when a chain owner decides to transfer some money. And execute message is when we receive a cross-chain message from another chain. What are we going to do with that message, basically? So let's start from initialize. And since we haven't specified any initialization arguments, we're just going to hard code that whoever built the application, whoever first deployed it, is just going to get 1 million tokens. And then the individual that created the application can distribute those tokens. So let's give the creator of the application 1 million tokens. To do that, we're going to do if let sum owner equals we're going to use the context of the initialization to get the signer, which is the creator of the application. And we're just going to say self dot initialize accounts. And we're going to pass the owner here and the amount we want to give them. So we're going to use amount from string. We have a nice little parser for amounts, which allows us to write it nicely like this, 1 million, but it has underscores, so it's more readable. And then I know this parses, so I'm just going to unwrap it. Import. And then we're going to, since this is an asynchronous function, we're going to await it. And finally, we're going to say, okay, execution result default. And we need to import from string here. So we're just going to do that quickly. So this just imported, where are you? From string here, use std str from string. Perfect, so that's our initialization method done. Next, let's think about our operation execution logic. So the first thing we want to do is we want to match on the operation. Since we're using it, we're going to remove the underscore. Match operation. And we are going to, we only have a transfer operation, so that's kind of easy, done for us. Whoops. And let's destructure this quickly. Add missing fields, cool. So the first thing we want to do is we want to make sure that the person who, well, the account that's trying to perform the transfer is authenticated to do so. So we'll use a method which we haven't actually written yet. It's called check account authentication, which is going to take the signer of the operation, authenticated signer, and the owner of the transfer. So we don't want to be able to send money from someone else's account, only from our own account, that is money that we own. So we check that the person who has signed this operation is indeed the person who we are asking to essentially debit money from. Okay, this is also a fallible operation, so we're going to add a question mark here. And let's quickly define the check account authentication method. So we're going to quickly do impl fungible. And we're going to define function check account authentication, which takes an authenticated signer, which is optionally an owner, and an owner. Okay, perfect. And this is going to return a type of result, and which is void and error. So very simple logic here. If authenticated signer is equal to the owner who we are transferring money from, let's return OK. Otherwise, we're going to error with the error incorrect authentication, which doesn't exist yet. We'll rename this to error, and we'll add the variant incorrect authentication, which is just, it's just, it has no content. Error. Okay, perfect. So that's our check account authentication done. Why are you complaining here? Okay, I think, again, this is just my ID complaining, seeing ghosts here. Okay, so once we've checked that we are authenticated to debit money from this account, we can go ahead and debit that money. So self.debit, debug, the given owner for the given amount. Again, this is debit is the method we defined back here. Self.debit. This is asynchronous, so we'll await it. And finally, we will send a cross-chain message to finish the transfer to the account. So we're going to send a message to the other chain saying, yep, you can credit that person. So we're debiting ourselves and we're crediting the other person on the other chain. self finish. We haven't defined this method yet, but we will in a second. Finish transfer to count and amount target count. And this is going to be an asynchronous method, even though we haven't defined it yet. Awesome, so that's our operation transfer done. One thing we're going to do is we're going to format our code just to make it a little bit prettier. There we go. And let's quickly define the finish transfer to account operation. So in our implementation of Fungible, we're going to define an async function, finish transfer to account. We're going to take a mutable reference to self. We're going to transfer a certain amount, and we're going to transfer it to a given account. And we're going to return an execution result of type message. This is message in Fungible. So to finish the transfer, what we're going to do is, first of all, we're going to check, because if we're sending money to the same chain, that is, if we're sending money on our chain, all we're going to do is just credit the amount in our state. Otherwise, we're going to send a cross-chain message to chain B to credit the account on the other chain. So if the chain ID of the account that we're sending money to is equal to this, it's called the system API, current chain ID, and this is just a Linera API which exposes, for example, the name of the current chain. We're going to self credit the account owner on our chain by the amount. And we're going to await, because this is asynchronous. And we're going to return the default execution result here. Else, we're going to create a cross-chain message, equals message credit, and we're going to send it to the owner account.owner. The amount is the amount that we've defined in our function, and we are going to return the default execution result, but with a message going to the target chain.chain ID, so the account chain ID, and we're going to give it the cross-chain message that we just wrote. Okay, perfect. So that is the finish transfer to account method done. Okay, and the final piece of logic in our contract is going to be dealing with incoming messages. So we're going to be consuming this message. I'm going to remove the underscore in front of it. And we're going to match on the incoming message. Again, we only have one variant, credit, and this has an amount and an owner. Yep. And basically what we're going to do is, so imagine now we're chain B, and we've received a message that we can credit a given owner in our state with an amount. It's usually going to be us, so we're going to do self.credit owner amount.await, and we're going to return the default execution result. And that is our contract logic done. Okay, we've written a lot of code, and we haven't actually tested if anything compiles yet. Spoiler alert, it doesn't, because we're missing a bunch of annotations on the types that we've defined. I just didn't want to put them in the beginning because I think it would be a little bit too much. But let's go back into librs and define all of the derives that we need to make things like operation and message serialize and be able to send them as messages and store them in our state. So for operation, we're just going to add debug, which we're going to use for debugging our application, deserialize and serialize. So I'm going to need to import those, use serde, deserialize goes first, serialize, okay. And our message is going to have the same set of derives, debug, deserialize, and serialize. And our account is going to have a few more derives. So we're going to be using clone, copy, debug, deserialize, EQ, ORD, partial ec, and partial ORD are used because this is going to be used in a map. And serialize and input object are again, well, input object is an async GraphQL trait. We'll get to that later. In fact, I won't use it right now because it's not really necessary. So these are the derives that we need in our types, and now we're gonna let the compiler tell us what we've done wrong. Okay, so we have 4 errors. Default is not implemented for message. Okay. From insufficient balance error is not implemented for error. Okay. Let's see. So let's start with the easy one. I forgot on line 52, I forgot to remove the underscore in front of context. That's an easy one. Let's go again. Okay, another 4 errors. I misspelled authenticated signer, as you do. From insufficient balance error is not implemented for error. That's fair enough. What we need to do there is go to our error enum and add an insufficient balance variant from insufficient balance error and just name this insufficient balance. Okay, 2 more messages here. State.rs line 31. Yeah, that's not, that is not into, that is insert. My bad. And the last thing is the trait bound message default is not satisfied on contract. Right, because, yes, okay. So fair enough, we don't have a default implementation for session call result, and instead what we're going to do is we're going to add an error variant here letting callers know that sessions are not supported. Sessions not supported. Yep, sessions not supported. We're missing a comma here, and this should just be error, sessions not supported. And there we go. We're getting a lot of unused errors from the compiler, but this is fine. Again, it's not picking up that some of these guys will in fact be used. So what we want here is to add, what is it, the unused annotation. Yeah, it's allow dead code. So we'll add it here, and we'll add it in our state as well. Okay, awesome. And we're just going to remove register view here as an import because it's not being used. And finally, in state line 29, for some reason it's saying mutable isn't necessary, which is strange. Huh. Ah, right, because this is meant to be saturating add assign, not saturating add, because saturating add returns a value, I think. And perfect. We're compiling, and we fixed all of our warnings. So the final step in building our application is defining our service. The service is defined by the service trait, which exposes a single method, the query application method, and a couple of associated types, the error type and the type of storage. And this has all been set up automatically by Linera project new. So to query our application, what we need to do is we need to build a GraphQL schema from our state and expose that to the node service. So basically, let's say we have a front-end web client. The workflow that you should imagine is the front-end web client builds a GraphQL request that gets passed into the node service, where it is forwarded to the application. The query is serviced, and the result goes back through the node service and to the web front end, where it's essentially presented to the end user. So, okay, the first thing is we're going to change the result here to a response type, the async GraphQL response type. And the next thing we want to do is we want to build a schema from our application state. And to do that, we're going to use the schema build command. Now, schema build takes in 3 arguments. The first is the query type, the mutation type, and the subscription type, corresponding to the 3 different types of schemas that GraphQL supports. Again, for more information on the details of GraphQL, you can refer to the GraphQL website and documentation respectively. So the schema we're going to give it is self. I'm going to clone it because it needs ownership over the query type. We're going to give it a mutation root, which we will define in a little bit, and an empty subscription because this application doesn't support subscriptions. And we're going to say finish to actually build that schema. Now, as the application comes in, we want our schema to process that application and read the state, process the application, and give back a result. So to do this, we're going to do let response equals schema.execute. Execute the request, which we're going to call your request. And finally, this is an asynchronous function, so we're going to await it. And OK response. And it's that simple. We haven't yet defined our mutation root, which I'm going to do right now. So struct mutation root. And the mutation root is going to tell clients which are querying the application, hey, what is the set of operations that this application exposes? At some point, this will be code generated, but right now we just have to build a function which corresponds to our transfer operation, essentially. So we're going to call this function transfer. It's going to take a reference to self because we're not really mutating any states. Takes an owner. What else? Yep, amount. And target account, which is of type count. Cool. And this returns a vec of U8. And it really doesn't like this. What don't you like? Oh, yeah, this is meant to be impl. Yeah, not bad. And we need to define the structure. Struct mutation root. And this is just going to be unimplemented for now. I'm going to just codify the code quickly so that it looks a little bit better. Perfect. Let's import these types. And what don't you like here? Again, size. This is my ID hallucinating. So all we're going to do here is we're going to we're going to create a new operation, serialize it into bytes, and return it and just return it. So BCS 2 bytes. BCS is a serialization format that we used. It stands for binary canonical serialization, and it's really, really cool. It's quite small, and also it ensures that bytes are, every time you serialize a structure, you're going to get exactly the same bytes, which is really, really useful if you're using those bytes in blocks and you take hashes of those blocks and you want them to be consistent, even if the underlying data, the ordering is not well defined. So BCS 2 bytes, owner, amount, target account. And then we're just going to unwrap this because I know that it works. So, oh yeah, we need to create the transfer operation here. So operation transfer. Okay, and we should be good. So let's cargo build this and see what happens. Okay, we're not good. Oh yeah, okay. So what we haven't done yet is we haven't defined that our type here in librs, our account type is an input object. And basically this is generating code that such that this account type can be used as an input in GraphQL. And I'm probably forgetting something else, and I think that is so the mutation root needs to be also an object. Again, this is just the code generation so that it's explorable by GraphQL. Let's cargo build again. Right, the object annotation is meant to be on the impl block. Oh, right. I need to change the ABI of the, yeah, I need to change the ABI here, which I forgot to do. The query is a request, a GraphQL request, and the response is a response. And we're done. Our application builds. Now let's deploy it to the network and actually transfer money from one account to another. Okay, so that's it for our first workshop. We covered quite a bit of ground today. We downloaded the Linera binaries. We created a local network. We created our first Hello World application, which we published on the network. And we started building out our fungible application. We implemented the core state logic, the contract logic, the service, and so on. And now it's ready to use. In the next workshop, what we're going to be doing is deploying it on the network and transferring funds from one wallet to another using the fungible application. And we'll also be making it a bit more robust by adding things like logs. We'll be adding tests and so on. So tune into the next one to see how that works. Thank you. Okay, so that's the first workshop. Oops, one sec. So yeah, I mean, if you guys have any questions, I'm more than happy to answer them. I'll stick around for a few minutes. I saw there were already some questions in the chat, which have been, I think, addressed mostly. I hope so. Is this chain good for games? Yeah, I think we talked about that one. Depends on the game. I mean, if you're running, yeah, if you wanna build a first-person shooter, and the part of the collision physics are on chain, it's probably not gonna be super fast. Can we use the mainnet now? No. So basically, right now, we're working on the DevNet. So if you want to build an application on Linera, you need to use the Linera binary, as we kind of showed in this workshop, to spin up a local network with a single validator and develop against that. Yeah, we're currently working on the DevNet as we speak, and then it's going to be testnet and then mainnet. But we're a little far off from that just now. Okay. Okay, well, if there are no more questions, yeah, we'll call this one a day. The next one's coming soon, the next workshop. Yeah, we're going to be adding some tests, adding some logging, actually using the fungible application to transfer funds and so on. So yes, stay tuned for that. Is there any DEX or DApp we can try now? Well, yeah, I mean, so what you can do is, if you take a look at the Linera GitHub repository, and I'll put in a link now. I'll just put a link in the chat. If you look under examples, there's a bunch of example applications that you can check out for different dApps that we've built internally, and you can try them out if you like, or you can build on them. Forbidden. Shouldn't be forbidden. Are you sure it's forbidden? I'm not getting forbidden on... I think it's the right link. It's strange. Okay, well, yeah, if there's any more questions, feel free to reach out on Discord. And I think we'll end the stream there for today. Thanks for tuning in, and yeah, see you guys soon.